Hi there. In this section of notes, we're going to take a little bit of a detour for a moment from, I'm just going to move that off of Millikan's face. We're going to take a little bit of a detour from a moment from talking about models of the atom to talk about this experiment this guy named Millikan does. And Millikan actually does come back again later in quantum mechanics, because he's the guy that does experiments, and he has all these neat little tricks that he's got and stuff that he does. So we will come back to him, but for now we're going to look at an experiment that he does that kind of grows off of J.J. Thomson's work, because we have to think about where J.J. Thomson leaves things. He knows there's these little negative charges apparently floating in some positive goo. And he knows that they have a charge to mass ratio of about 1.76 times 10 to the 11 coulombs per kilogram, which means they must be really tiny masses. But he doesn't know the charge or the mass. Now, if only somebody could come up with an experiment that would let you measure charge or mass, then you would be able to stick it into the charge to mass ratio number, and you'd have the other one automatically also. And that's exactly what this guy, Robert Millikan, is going to do for us. So in the experiment, what he sets up is what to us is really, again, parallel plates. It seems like we're always doing parallel plate stuff. Now, significantly, the bottom plate is going to be negative and the top plate is going to be positive. We'll see why that's important in a moment. But you can also see in the top plate, I'm trying to show you that we've like drilled a hole right down through the middle of the top plate. Now, the hole itself actually wouldn't be that big at all. You would not be able to fit your pencil necessarily through it. Maybe more like the lead of your pencil would go through. It was a rather small opening though. Now, off to the side, he has a device called an atomizer. An atomizer doesn't make atoms, just so you know. What it does is it takes any sort of a liquid and it mists it. So imagine, and this is the way I kind of tried to draw it for you there, it's an old school perfume bottle where you've got the liquid in the bottom, and then the ball part that's there, you go, you squeeze it, and it sprays out perfume from it. Except in his experiment, that's not perfume, it's mineral oil. Now, most of you will have actually seen mineral oil at some point. If you've ever used baby oil is mineral oil with some fragrance added. So that, like, after a baby has a bath, you put baby oil on them so their skin doesn't dry out. That's mineral oil with the fragrance added. So you might say, why is he doing this? Well, he can get very discrete droplets, but more importantly, on that atomizer he's got, the tip that's there is made out of metal, and as the mineral oil squirts out, as it gets out of that nozzle, it actually gains a charge. He doesn't know what the magnitude of the charge is, but he knows that they tend to be negatively charged. Now, most of those droplets that are coming out, they're just going to fall onto the top plate, and that's the end of them. But totally by chance, some of those drops fall down through that hole until they get between the plates. Now, this is where we need a little bit of luck, because we need the electric field to be just right with the mass of the oil drop to be just right, so that the electrostatic force pushing up on that negative mineral oil drop and the force of gravity pulling down balance. F net equals 0. And if everything is just right, the oil drop just floats there, just for a moment. Now, I can tell you, I did this experiment in university, and it is not fun, because heck, I could even rig the experiment a bit because I know the charge of electrons, and I could set it up assuming, oh, I'm going to try to catch oil drops that have, like, let's say 3 extra electrons on them, and I could approximate what the size of the oil drops would be. So I would try to rig the experiment to try to catch those. And even then, it was miserable difficult to get them to float like this. Now, Millikan had to do this experiment like thousands of times just to get a few of these oil drops, purely by chance, to float. How did he know they were floating? How could he know things like the mass of the oil drops? Because off to the side, he had what looked kind of like a little telescope, and you can see I've marked little lines on it. Those are called hash lines. So when you're looking through the scope, you see all these dashed lines, and they're actually measuring like fractions of a millimeter. When you look through, you can see the oil drop if it's floating. And because you can measure using those hash lines its diameter, and it's pretty much spherical, and you know the density of mineral oil, you can actually calculate its volume, and from that its mass, and then you can calculate Fg. And if you know Fg and you know it's floating, you also then indirectly know Fe. And that's basically what he was doing. Now remember, in this experiment, we don't ahead of time know for sure how many excess electrons are on there. It could be 3 or 5 or 16 or whatever. We know that the oil drops themselves have bajillions of electrons and protons, but all that we care about are the few excess electrons, extra electrons that it's gotten charging by friction going through that metal nozzle. So what this allows us to do is, like before, say that F net is 0 so that the magnitude of my two forces are equal to each other. They're opposite in direction, but the magnitudes are equal. On the left-hand side, I can put in QE, because if I take the electric field formula and I solve for electrostatic force, I get that. And on the other side, FG just equals mg. It's just regular force of gravity pulling down on the oil drop. Now, depending on exactly what kind of a question you're doing, quite often you're going to have to substitute in another formula for electric field, because probably what we're doing is we know the voltage on those plates and we know the distance between the plates. So where E is for electric field there, we would substitute in V over D. And then it's just a matter of finishing up the manipulation. I'm going to multiply both sides by D and divide both sides by V. And I have a formula that lets me figure out Q, the charge. I need to know the mass, not of an electron, but of the oil drop, something that even though it's really tiny, it's big enough I can measure. G, good old-fashioned gravity. D, the distance between the plates. And V, the voltage that I've got on the plates. So I tell you that we're doing a Millikan type experiment, and that because I did all that stuff with density and measuring the size of the oil drop and its volume and all that, I know its mass is 3.3 times 10 to the negative 15 kilograms. Watch out. Quite often you're going to be given that number in grams, and you're going to have to like change it into kilograms, so or something else. So watch out for that. I know the distance separation on my plates and the voltage I was using. So the question asks, we have to be careful about this, how many excess extra electrons are on the oil drop? So I would go ahead and I'd set up my formula and do all that manipulation and stuff, and I go ahead and plug in my numbers to find the charge. So I stick in all those numbers, I do all my calculations, being careful because the distance was in centimeters, so I divided it by 100. And I go ahead, I calculate it, and I get this, 9.0 times 10 to the negative 19 coulombs. The question didn't ask for the charge on the oil drop. It asked how many excess electrons are on the oil drop. Now, those are the extra charges that are giving that oil drop enough charge that it could float in between the plates. So I look at that number that I've got for the charge, and that's not going to be my answer. What I'm going to have to do is do a quick little calculation. I can set it up as a ratio if I need to, where I say I know the charge of the excess charge on my oil drop, and I know that each electron has 1.60 times 10 to the negative 19 coulombs per electron. I take that and I do the math, and I find out, I get the number 5.65, a bunch of other digits, electrons. Now, can I truly have fractions of electrons? No, this is due to experimental error. So I do what I'm supposed to do. I round this off to the nearest whole number using regular rounding rules. Because it's 5.6, that means it'll round up and I must have 6 electrons. That's my final answer. So on that particular oil drop, there were 6 excess electrons. There's really majillions of electrons and protons, but those numbers are mostly equal and balance out. It's the 6 extra electrons that gave the negative charge to the oil drop, so it would float. There's a few questions you can try from the textbook, so good luck with that.